Section 2 is dynamics of uniform circular motion. So we're extending the learning that we did in Section 1 by starting to do some problems. So because objects moving in circular motion are accelerating, like we talked about, they must have a net force acting on them. So F net equals ma, like we learned. This is Newton's second law. And so that A that we learned about in the last section would be mv squared, v squared over r. So we substitute the A here with v squared over r, and we wind up with mv squared over r, okay? So we're just taking the formula that we used in the last section and substituting it in here, and we have now the force equals mv squared over r. So this force is directed toward the center of the circle and produces the centripetal acceleration of uniform circular motion. So the acceleration is directed toward the center of the circle, so that means the force is directed toward the center of the circle. So in other words, a particle of mass m moving at a constant speed v around the circle of radius r must always have a net force, and that net force is going to have this magnitude, mv squared over r, pointing toward the center of the circle. So without this net force, the particle would move off in a straight line tangent to the circle. And I want to talk about that real quick. The word tangent here is not like the tangent, secant, sine, cosine that you have seen in geometry. This is, the word tangent means I have a circle here, okay, here's my circle. This line is tangent to the circle. It touches the circle one time, okay? So if I am moving along the circle, like imagine you're spinning a rock on a string or something, okay? You're spinning it around and around and around, and then all of a sudden the string breaks, and it breaks right there, okay? So we're spinning around and around and around, and the string breaks right there. What's going to happen, okay? So at that moment in time, when the string breaks, that rock would have a velocity vector pointed in that direction. The string breaks at that moment in time right there. That means that rock is going to take off tangent to the circle along that velocity vector right there, and it's going to move in that direction, okay? So without that net force anymore, the net force would have been directed along that string toward the center of the circle, okay? That would be a tension force, right, along that string. So that string breaks, that tension force is gone, okay? So now it's going to go, the rock is going to go tangentially along that velocity vector in a straight line tangent to the circle. So directly along that velocity vector right there, okay? And that line that it's following was tangent to the circle. So that word right there, tangent, means touching the circle one time, okay? So that's a very important word that you understand. Okay, so engineers design curves on roads to be segments of circles. We actually do that so that we can model mathematically the situation that's going on, okay? Also, the dips and the peaks in the roads that you have, so like hills and peaks in the roads, are also segments of circles with a radius that depends on the expected speeds that vehicles will be driving over them, and along with other factors too. But those are designed specifically with those speeds in mind so that we can have some sort of safe speed expectation for the vehicles as they travel over them, okay? And so, like if you're ever driving along and the speed limit's 70 miles an hour or whatever it is, and then you see these signs that say speed limit, curve ahead, speed limit now 55 all of a sudden, and you wonder why that's the case. It's because the road is not designed to handle the speeds that you are currently driving. So they require a slowdown so that you can safely navigate the curves or the hills or whatever it is without losing control of your vehicle, because the road was not designed for the speeds that we're driving now. So that's why. Anyway, okay, so we have a car moving at a constant speed, goes into a dip in the road. At the very bottom of the dip is the normal force in the road of the car greater than, less than, or equal to the car's weight. So, okay, what we want to do is we want to draw the dip in the road. So the dip is this situation, okay? Now I'm super exaggerating this, okay? This is no way that the road looks like that, but so I'm exaggerating that, okay? But it is supposed to look circular, okay? Now, the car is currently at the bottom of the dip. So here is the car. And obviously, I'm just modeling that with a circle, okay? Now, at the bottom of the dip, okay, we're modeling this with a circular motion. At the bottom of the dip, what are the forces acting on the car? Okay, so we're going to have weight down, and we're going to have normal up. Okay, normal up. All right, now the question is the normal force of the road on the car greater than, less than, or equal to the car's weight? Ignore the way I drew the arrows. It has nothing to do with anything. Okay, so if you're understanding the concept of what we're doing here, this is circular motion. And in circular motion, we're going to have an acceleration towards the center of the circle. The center of the circle is up here. There is an acceleration toward the center of the circle, which means we have a net force here, which we didn't write down yet. F net is toward the center of the circle. And if we have a net force toward the center of the circle, that means that the sum of the forces must eventually be pointing up. And if that's the case, then the normal force vector must be longer than the weight vector. And if that's the case, then to answer the question, is the normal force of the road on the car greater than, less than, or equal to the car's weight? The normal force must be greater than in order to give us this F net up, okay? Now, if the car was over here, totally different story. Car is over here, totally different story. It's at that exact moment in time, the normal force is pointed up and the weight is pointed down. So we have this alignment along the axis, and that gives us the F net aligned with those vectors. And so therefore we can say the normal force vector is longer than the weight vector. And so therefore the normal force is greater than the weight of the car. Okay. A car is turning a corner at a constant speed, following a segment of a circle. What force provides the necessary centripetal acceleration? Okay, so here we want to kind of draw a sort of a pictorial overview of this one. The car is turning the corner at a constant speed. So we draw the curve. The center of the curve is somewhere over here. The car is on the curve. So here's the car. Okay, the car is going along this way, maybe. So that would be a velocity. So we put a V there. Now, what force provides the necessary centripetal acceleration? So the centripetal acceleration would be pointed in, right? Now, there's going to be a force there that provides that centripetal acceleration. The question is, what force is that? It can't be a tension force because it's not connected to anything, right? The car is just driving around the curve. So what force is doing that? The correct answer is it's a static friction force. Friction from the tires on the road is what is allowing this car to make its way around the curve. If there was no friction, the car would just skid off, okay? If you got bald tires, the car skids off. If you're going too fast, the car skids off. And skidding is kinetic friction. So what is allowing us to stick to the road? Static friction. So it's static friction as we go around the curve. Okay. Now, in the direction of the velocity, it's a different friction that's allowing us to move forward relative to the car. But going around the curve, what is preventing us from skidding off? It's static friction. Okay. So hopefully that one made sense. Now, solving circular dynamics problems requires some discipline. So these are your steps for solving circular dynamics problems. Circular motion involves acceleration and therefore a net force, okay? So we're going to use the techniques that we used back when we were doing Newton's second law problems, like F equals ma, some of the forces in the x direction, some of the forces in the y direction, that stuff. So acceleration is directed to the center of the circle, caused by a net force directed at the center, brought about by one or more forces that we're familiar with, like tension, weight, friction, like we just talked about, okay? So we got to remember that. Now we're going to draw a visual overview by sketching the motion, defining symbols, defining axis, identifying what's to be found, like we've always done, okay? Now, there's going to be two common situations. We're going to have motion in a horizontal plane, like on a tabletop, okay? Like you're spinning something around on the surface of a table, okay? You're going to draw a free body diagram with the circle viewed edge on, like you were down at eye level with the thing that you're spinning around on the table. And you're looking at the circle edge on, okay? You're going to draw the x-axis pointed at the center of the circle and the y-axis perpendicular to the plane of the circle. So let me see if I can sketch that on here real quick. So you're spinning something around. So here's the center of the circle. We're looking down the table, okay? We're not looking above and watching the thing spinning around. We're looking eye level on the table. Here's the center of the circle. And here is the object over here, okay? We're going to take the x-axis and point the x-axis toward the center of the circle. And we're going to take the y-axis and make it perpendicular to the x-axis, okay? Or we're going to say, here's the object over here. We're going to take the x-axis and point it to the center of the circle and the y-axis and make it perpendicular, okay? You see how that looks just like every other axis that we've ever drawn? Okay, so that's if we're in a horizontal plane. If the motion is in a vertical plane, so like a Ferris wheel, we will imagine like we're looking straight at the Ferris wheel. So we're looking directly at the circle. Okay, so draw the free body diagram with the circle viewed face on. So it's like we're looking directly at the face of the Ferris wheel. Okay, so now the x-axis is going to be pointed at the center. So maybe the car of the Ferris wheel is right there. We're going to draw the x-axis pointed at the center, and we're going to draw the y-axis tangent to the circle. There you go. Okay, so that's always, we're going to wind up with the x and y axis like we've always drawn them. All right, so that's the idea. So now solve. We have Newton's second law for uniform circular motion. Here is that formula again, mv squared over r. Is the equation directed at the center of the circle? Let me scroll up here. Okay, so then some forces act in the plane of the circle, some act perpendicular to the circle, some may have components in both directions, and we'll see an example of that here in this section. Depending on the problem, we're either going to use the net force to determine the speed, so that would be v, and then use circular kinematics to find frequencies or whatever other details they're looking for. Or we will use circular kinematics to determine the speed first and then solve for unknown forces, okay? So our connection here is speed in both cases, all right? So we're going to get some examples and then we'll be done. So kinesiologists are scientists who study human motion, can measure the forces that act on runners as they round a curve. So the forces on a runner's feet are vertical normal force that on average serves to counteract gravity, and a static friction force parallel to the ground pointing toward the center of the runner's circular path. So the average value of this inward pointing force is measured to be 600 newtons for a 75 kilogram runner rounding the curve that has a 2.5 meter radius. What is the runner's speed? Okay, so we want to write down the things that were given. We want to draw like a free body diagram and then solve, okay? So we're told that the runner's mass is 75 kilograms. We're told that the static friction force is 600 newtons. And we're told that the track, or whatever it is, so the radius is 2.5 meters, okay? Now, this is happening obviously on a horizontal curve. So we're going to draw the center of the circle over here. The runner is over here running. So here is the x-axis and here is the y-axis. And then we're going to have a weight down, a normal force up, and then a static friction force that's allowing us to make our way around the curve, F sub s. All right, now there is also a F net. If there wasn't an F net, we would not be making a curve. And that F net is pulling us towards the center of the circle. Okay, so now all we need to do is the sum of the forces. Really all we care about here is the sum of the forces in the x direction. Okay, so sum of the forces in the x direction. The only force in the x direction is F sub s equals mv squared over r. Okay, well, we know F sub s, and we know m, and we know r, and we're looking for what is the runner's speed. So we're just looking for v here. Very straightforward. We just solve for v. So multiply both sides by r. We have F sub s r, divide by m, and square root, and we have v equals that. We can plug all that stuff in, and we'll have our answer. So v equals square root. F sub s, they told us was 600 newtons. R, they told us was 2.5 meters. And M, they told us was 75 kilograms. And we can plug all that stuff into our calculator. And in the end, we wind up with 4.5 meters per second after significant figures. That's it. Okay, so we move on. What is the maximum speed with which a 1,500 kilogram car can make a turn around a curve of radius 20 meters on a level unbanked road without sliding? So this is the turn like you would expect to see in a major intersection in a city. So very similar. Okay, so like a pictorial overview maybe first. This is basically what we were talking about earlier with the curve and the car and the velocity and the center of the curve over here and the centripetal acceleration going this way. Okay, so we have velocity here. We have the radius of the curve was 20 meters. We have mass, 1,500 kilograms. And we're looking for Vmax, the maximum velocity that we can go. Now, also, we're talking about without sliding. So that means we must have a static friction situation going on here. And so the maximum speed means we're going to have to hit mu sub max, a maximum static friction force. So we need F sub s max. So we need mu sub s here. And when we go look that up, it winds up being 1.00 actually. Okay, so, which by the way, you can find that in the sheet that I gave you with all of the constants in it. So here we go. If we draw a free body diagram of this situation, again, we have the center of the circle. We have our vehicle. We have the x-axis pointed towards the center of the circle. We have the y-axis perpendicular to that. We have, for our vehicle, the weight down, the normal force up. We have the static friction force directed towards the center of the circle, F sub s. Okay. Now, we can do the sum of the forces in the x direction. This is the x direction here. This is the y direction here. So, sum of the forces in the x direction equals F sub s equals mv squared over r. Looks familiar. But this time, because we have the mu sub s sitting there, we need to also talk about the sum of the forces in the y direction. And that is going to be the normal force up minus the weight down equals 0, because we're not going up or down here. So that means the normal force equals the weight. And the weight is mg, so that equals mg. Now, by the way, in this figure, we have an acceleration going off to the right. So we have F net is to the right. And that's why we had the mv squared over r. Now, we know from earlier in the year that f sub s max, when we have f sub s max, we will be able to say mu sub s n. We cannot say mu sub s n unless we are looking for the maximum possible static friction force. The maximum possible static friction force will happen when we have our maximum speed going around the curve. So this is what we're looking for here now, okay? Then the normal force is actually equal to mg. So we have now mu sub s mg. Okay, so now f sub s max can be plugged in at the top here in the sum of the forces in the x direction, because really f sub s has to be f sub s max. So now that top equation becomes mu sub s mg for f sub s equals mv squared over r. Now I see that there's m's on both sides, so those m's divide out. And I'm looking for the fastest possible speed. So I'm going to solve for v by multiplying both sides by r. So I have mu sub s g r. And then I just have v squared on the right-hand side, so I'm going to square root both sides equals v. And now I can plug everything in. I know all that stuff on that side. So I have v equals square root. Mu sub s is just 1. G is 9.8 meters per second squared. R, they told me, was 20 meters. Okay, and when I plug all that in, I wind up with, after significant figures, 14 meters per second, and that's it. Done. So we can go 14 meters per second around this standard curve at a major intersection in a city. Double it and add a little, probably about 30 miles an hour. I don't think that would be very safe in a major city, but you can go about that fast. Okay, a curve on a racetrack of radius 70 meters is banked at a 15-degree angle. At what speed can a car take this curve without assistance? All right, so this one takes a little bit of thought to set up. Again, this is a horizontal curve. That means we want to represent this situation with a horizontal setup. So we have our curve, we have our vehicle, we have a horizontal axis for x, we have a vertical axis for y. But the track is banked. So what we're going to do is we're going to tip at our angle theta. I'm going to leave it as theta for now. I know it says 15 degrees, but I'm going to leave it as theta. And then we're going to also show that perpendicular theta as well. Okay. So now let's fill in some stuff. We know that our car has a weight down. And we know that we have a normal force, but the normal force is going to act perpendicular to the road. So that normal force goes along that tip. So that's N. Okay, so now what we have always done is broken the vectors into components. We need a component in the x direction because we're talking about without assistance from friction. So there is no friction on this track. So that means we're going to be only talking about what kind of assistance does gravity give us to come around this curve, okay? So that means we need to break these vectors into components. Now what I'm going to do here is I'm going to break the normal vector into components. So I'm dropping this line down here to create my angles. So I have this angle theta sitting down here, right there. And then parallel lines are going to give me my angle theta sitting right there as well. Okay, so this looks kind of confusing, but that theta right here is actually way down here. So this theta is up here in the corner. Okay, so now I need to come up with my normal vector in the x direction right there. And that is opposite my angle theta inside the triangle, so that's going to be sine. So sine theta equals normal in the x direction, opposite, and then times divided by the hypotenuse, which is the normal. So normal in the x direction equals normal sine theta. Okay, and then the normal in the y direction we found the same way, except it's going to be cosine theta equals normal in the y direction over normal. So we'd have normal in the y direction equals normal cosine theta. Okay, so we're just going to work with the normal vector here, no problem. Okay, so now we can do the sum of the forces in the x direction. I wrote y. We're going to do x equals. So the only force in the x direction is that normal component in the x direction. Normal in the x direction, though, I just said is normal sine theta. Okay, now there is acceleration in the x direction because we have an F net going that way. Okay, so this equals mv squared over r. Okay, we're going to leave that like that for now. And we'll do some of the forces in the y direction. Equals. So we have the normal in the y direction up, but the normal in the y direction up is just normal cosine theta. And then minus the weight equals 0. Weight is mg, so when I'm going to move that weight over. So I have normal cosine theta equals mg. So now what I'm going to do is I have two equations here, and I'm going to solve for normal in the y equation and then substitute it into the x equation. The reason I'm doing that is because we want to solve for speed. So that will leave me with just theta, which I know, mass, which I don't know, but it's not going to matter, and g, which I know, radius, which I know, and v, which is what I'm looking for, okay? So solve for n. N equals mg over cosine theta. Okay, now we're going to plug that into the x equation up here for where sine theta is. So now we have mg sine theta over cosine theta equals mv squared over r. And now you should see that the m's divide out. And also, we have sine theta divided by cosine theta, which is tangent theta. I'm going to solve for v now. So I have multiply both sides by r. I have g r. Sine theta divided by cosine theta is tangent theta. Okay, equals, and I just have v squared there. So if I square root both sides, I have equals v. Okay, I know g, I know r, I know theta, so I can plug everything in. I have v equals square root. That'll be 9.8 meters per second squared. R, they told me, was 70 meters. Tangent, theta, they told me, was 15 degrees. So we can type all this into our calculator, make sure you're in degree mode. And we wind up with, after significant figures, it winds up being 14 meters per second. So, with no friction at all on the track, you can go 14 meters per second around that curve and not slip. So basically what this is saying is, of course there's going to be friction on the track, but because the road is banked at a 15-degree angle, you actually get a 14 meter per second assist from gravity because of the bank. So you can go that much faster without having to worry about slipping on the track. 14 meters per second would be 28 plus some, so 30, maybe 32 miles per hour extra just because of the bank. Pretty nice. Okay, we're getting there a little bit more. Maximum walking speed. So humans have two basic gaits. A gait is like a tempo to the way that you walk. So you can walk and you can run. So how fast can you walk? There actually is a limit to the speed at which you can walk. And this limit is set by the physics of circular motion. So as you walk, if you look at the picture, your leg that you are walking over sets a radius. And it stays that way the entire time. Your hip arcs over the top of your leg as you walk, and your hip winds up moving with a velocity, a speed, okay, according to circular motion. And then you plant your front foot, and then you walk with a circular motion over the top of that next leg, and so on. So that is walking. Running is a different story. It doesn't follow the same circular motion. But if you are walking with a walking gait, then you are following the circular motion, okay? Now, when your hip is directly above your foot, then your F net would be directed directly down, okay? So the circular motion then has this force directed directly to the center of the circle, which is directly over your foot, okay? So the force acting in the body in the figure here, at the midpoint in the stride, with the weight directed directly down, and the normal force is directly up, Newton's second law states this right here. Okay, the weight minus the normal would equal mv squared over r. The net force is directed down toward the center of the circle, and we have this free body diagram here. Okay, the normal is up, the weight is down, F net is down, so the weight vector is actually longer than the normal vector. Okay, this is kind of like what we talked about earlier. So if this is the case, now I'm going to slide this up. If this is the case, then in order for the net force to be pointed down, the normal must be less than the weight, right? Your body is trying to lift off as it pivots over your foot, decreasing the normal force exerted on you by the ground. The normal force becomes smaller the faster you walk, but the normal force can't be less than 0. So therefore, the maximum possible walking speed occurs when the normal force is actually equal to 0. So that means the weight would equal mg equals mv squared max over r, and if that happens, then we have v max equals exactly the square root of gr, which means the maximum possible walking speed is limited by r, which is the radius of your leg, and g, the free fall acceleration. So on Earth, g is g, right? We're staying on Earth, so that means we're limited by the length of your leg. So a taller person can physically walk faster than a shorter person, and that's it. Like, there is a limit to how fast you can walk. So a taller person with longer legs will always be able to walk faster than a shorter person or somebody with shorter legs. And that's just by physics right here. Okay, that formula right there proves it. So next time, if you're a short person and somebody taller than you with longer legs than you is walking next to you and you can't keep up, this is why. You have to switch to a run to keep up with that longer legged person. Okay, the last thing we're talking about here is a block on a string spins in a horizontal circle on a frictionless table. So this is all like the same block in these 5 different scenarios. Rank in order from largest to smallest the tensions, TA through TE, acting on the blocks A through E. Notice the numbers down at the bottom there. That's important. So since this problem is talking about tensions, what it's really getting at is acceleration. Because the greater the acceleration, the greater the force. In other words, the greater the tension, right? So what we need to do is figure out which one has the greatest acceleration on down to the smallest acceleration. So if you were to look at your acceleration formulas, since we see frequency and radius down here, the easiest thing to do would be to look at your acceleration formula that deals with frequency, and that is 2 pi frequency squared times the radius. And now in this formula, look at how it works. The frequency is being squared, the radius is not. So which one is more powerful here, the frequency increasing or the radius increasing? You should be thinking the frequency increasing because the frequency is being squared, okay? So a bigger frequency than being squared is really impactful, okay? So now, if I want to look at these numbers, I have the radius, the bigger the radius, the bigger the acceleration for sure, but the bigger the frequency, the much bigger the acceleration, which therefore means the bigger the force, okay? So the biggest frequency of all is E, and also it has the largest radius. So that means E is definitely the biggest tension, okay? So E is the biggest one of all. Now, after that, the frequencies all drop, but D has the same radius as E. D has the biggest frequency left over of all of them. So that means D is going to be the next biggest one. Okay, from there, if we look at the rest of them, compared to D, C has the same frequency as D, and it has the biggest radius of all of them that are left. So that means C is going to be the next biggest one. And then we go from there, what's left over? Well, B has the biggest radius that's left. Even though it has the same frequency as A, it has a bigger radius than A, which means that B is going to be next, and that leaves A as the smallest tension. So it actually went in reverse order, E, D, C, B, A. So that's how you do that. Always look for a formula or some other sort of like concept that you can use to help you get through these types of problems. In this case, that formula was perfect. Okay, that's it for the section.